All right, welcome to today's lecture. Let's briefly remind ourselves what we have been doing for the last couple of lectures, and in particular, in the very last lecture we have been beginning to look into the problem of how to realize behaviors for computer game agents. We looked at different kinds of behaviors. We saw that there is a natural hierarchy of behaviors, say from reactive over tactive towards strategic, and that on each of these levels, which we may think of when we think about behaviors, it requires more and more context or world knowledge to actually come up with appropriate behaviors. So for that reason we said, well, let's forget about the more complex kinds of behavior and let's focus on the problem of reactive behaviors and on the question as to how we could implement or equip virtual agents, computer game agents, with the possibility of behaving at least in a reactive manner. Now we saw different approaches, and last time we studied the idea of sort of rule-based behavior programming. And in particular we studied the idea of how we could come up with rule-based representations of behavior that are at least mimicking the way human beings, people, would think about the world, would reason about the world. So what we came up with was rules of the form, and here's just an example. If, what do I have here? Health is low. Health is low. And, say, enemy is close, then execute a script that could be called flee, certainly something appropriate to do in a situation like that. So what do we have here? Well, first of all, we recognize the structure of a rule. It is basically an if-then statement. And what this always does, and this is not just in the context of games, but in general, it checks a certain precondition. And depending on whether or not this condition is fulfilled, something will be done. The particular aspect about this formulation of this rule is that we express it in terms of attributes of game entities. So health would be an attribute of the non-player character itself, for which we are going to realize behavior here. In say, first-person shooter game, health is an important attribute of a non-player character. And an enemy is another game entity. And that game entity does have a position within the game world, on the game map, as does the agent we're actually interested in. So these are two further attributes. The position of the game agent and the position of the enemy could be the human player or another game agent. Both have locations, both are located within the game world, and those are their attributes. We can derive features from attributes like that, for instance, their distance. If we understand that location is, say, some three-dimensional vector in a three-dimensional game world, we just sort of subtract both vectors, take the Euclidean norm, and that then allows us, first of all, with respect to like these immediate attributes, or with respect to sort of derived features of attributes, to argue about what we have observed, whether health is low and distance is close. Now, this is exactly, careful here, this is probably how humans would argue about the world. Right? We do not really say if I am at GPS coordinates some two numbers and want to go to, I don't know, GPS coordinates some two other numbers, then I have to execute a succession of transitions between certain world coordinates. This is not how we argue about the world. We argue like if I'm standing sort of in front of the whiteboard, whatever that means, right? In front of the whiteboard is here, there's also here, is also over here. In front of is not really specific, but specific enough in order to argue and reason about what's going on in the world. Our question then was like, how could we do that? How can we implement these kind of reasoning processes on a computer? And while pondering that question, we studied the idea of fuzzy logic, fuzzy reasoning, and fuzzy control. And fuzzy logic is, to me, it's funny. This is one of these areas of computer science, mathematics, and say probably control theory. Like, so lots of areas of science, scientific areas actually could or should deal with ideas of fuzzy logic. But it's one of these topics that you either love or hate. It's powerful stuff. We can do a lot with that, and we saw that it's rather easy to do. Like once you get the gist of it, it's seriously very intuitive. Of course, lots of unknowns in there, how to choose these membership functions and stuff like how to choose the root. Nobody knows, but say with some expert knowledge or some world knowledge, some context, we can do that. And still, some people love it, some people hate it. It's one of these areas where you either do it or you don't do it. Right? Either you are a person that uses fuzzy logic for whatever, or you are a person that despises fuzzy logic and rather does everything in terms of probability theory. Those two things are different things. There is a certain relation. You can sort of map the one to the other. Be careful here. But the funny thing to me is, fuzzy logic is one of these things where we actually have schools of thought in computer science. Usually we don't have that. We are not in the humanities where we have, I don't know, theories, and you either subscribe to one theory or to another theory, because you cannot really actually prove these theories. You either believe in this one or in that one, unless something turns up that shows that whatever you are currently adhering to is like really not scientific anymore. So in other sciences there are these schools of thought. In computer science there usually are not, because in computer science we're dealing basically with mathematics in a sense, and in mathematics we can prove everything. We didn't prove stuff about fuzzy logic. We could show, like mathematically, that what we did last time, the way of using these ideas to inference, that makes sense, can be proven, right? And still, some people love it, some people hate it. And that is, like, make a long story short, why I consider it funny. I hardly ever use it myself. That is foreshadowing, because we will today transit to something else. Today we'll begin a study of how we could use probability theory in order to realize behaviors. But before we do that, I have to point out that what we have done so far is really just considering purely reactive behaviors. When we have been discussing these kind of rules, which we can understand as implementations of reasoning about states what is currently going on in the game world. We reason about those and derive actions from our reasoning. In what we have done so far, this has all been purely reactive. This is just with respect to the current state of the game world. So, and that is to say that so far we have not considered temporal context. We could do this, of course, using these kind of rule bases. How would we do that? Exactly. She proposed to include sort of timestamps into these rules. You could say if health at current time is low and health at previous timestamp was not so low, and something else, then do something. Right? So we can, of course, always extend these conditions. We could have, I don't know, several clauses dealing with health. Health right now, health at the previous timestamp, health at the timestamp before that, and so on and so forth. And of course, that would allow us to include temporal context into these rule bases. We will not do that. That grows quickly out of hand, and it's probably not such a good idea. It's totally possible, but maybe not the best way of doing it. So, therefore, we should think about other ways of including temporal context into behavior programming. In particular today, or well next, so it's not just today, next subject of study will be approaches towards what do I say here? Context-based behavior programming. Context-based behavior programming. Well, and when I'm saying context-based, and given what we discussed so far, it's basically temporal context. Right? Now, how could we do that? Given what we have discussed so far, we can, of course, again, think about rules that would somehow capture the idea of temporal context. Here is an example. If, say, enemy is trying to conquer base, then we execute a script that is called reinforce defense. Reinforce defense. Can you see that this rule is with respect to longer periods of time? Can you see that? It's even in the language, right? Using this round form here, which basically refers to things that are going on. It's not just, imagine you were a non-player character and guarding a base, and at a certain point in time, I don't know, an enemy appears in the entrance to the area you are supposed to guard. Well, you can react to that. But basically, from what we have done so far, you just see it appearing and you would react to that observation. Now then, if that enemy was, if you would observe it for a longer period of time, would either approach you immediately or, I don't know, run some path, whatever, you would have more observations available to reason about what the enemy is doing. It might, you know, appear and immediately run away again. That would definitely not be the act of trying to conquer the base. But if one enemy would appear and then another, and then they would spread out and then they would move towards you, then that would probably indicate that this team of enemies is now currently trying to conquer your base, the area you're supposed to defend. So with rules like that, sort of implicitly, if we check more complex conditions, such as enemies trying to conquer the base, then very implicitly and very intuitively, this rule incorporates temporal context. The question is, of course, how can we check whether or not that condition is given? So, question has to be how to do this. That part is easy. We can certainly think, like, whenever I put this in quotation mark, that sort of indicates this is a script that can be executed. Right? There could be scripts that would realize the behavior of reinforcing the base, whatever that implies. How could we check whether the enemy, be it a single enemy or actually a team of enemies, is trying to conquer the base? Any ideas? Yeah?
Maybe every time frame we capture the data, so the parameters,
yeah.
and then we try to update some status that would then accumulate this data over some time, and then some status would be very
Yes, this is exactly the right answer in a very roundabout way. No, this is, I mean, you have totally captured the gist of it. What you proposed was to observe attributes or features of the enemies and have some sort of state updates, and then after a couple of observations look at what state we are in and do something according to that. Right? I paraphrase that. So yeah, that is exactly what we are going to do. It's exactly what we are going to do. But as I said, this answer is perfectly right in a very roundabout way. How would we, do it like in practice? How do we implement that idea? And the answer, at least one answer to that question, is the use of hidden Markov models. And maybe you have already heard about hidden Markov models. That is a technique or a paradigm from the area of statistics. And it is extremely popular, and they are extremely popular and useful in areas such as machine learning or pattern recognition. Right? And now that I have dropped the term pattern recognition, this is of course a pattern recognition problem. The question if the enemy is trying to conquer the base. And why is that possibly a difficult problem? Right? So let's make up an example. Suppose that the entry over there would be, I don't know, the base that is about to be conquered, and I would be the enemy. And if I, as the enemy, would approach this location over there, so this is now the game world, our lecture hall is the game world, and I would approach it like this, and probably while approaching I would fire towards whoever is there, or I could approach it like, sidestepping, trying to dodge bullets, and still I would approach the base. Or I could, run very fast. I could, go over here, go like so. There are many different ways as to how I could try to conquer the base. At the same time, I, could probably go over here, go this way. And that would probably indicate that I'm not really trying to conquer the base. The difficulty here is that trying to conquer the base. Like once we see it, it's obvious, but it can have many, possibly infinitely many different instances. And so we are dealing with a pattern recognition problem. We might be observing a certain sequence of game states, or we derive a sequence of attribute measurements from these game states. It can happen that that would be a sequence we have never seen before as the non-player character, as the program that is realizing the intelligence for the non-player character. Can happen that we have never ever seen that particular sequence, and still we would have to derive a conclusion from that. And that is basically a pattern recognition problem. We have to deal with observations, and we have to map them to concepts. And the concept here is conquer the base. This is an abstract term for a behavior that spreads over several time steps. This is what we have to recognize, or we have to recognize not conquering the base, do something else. Now, all of a sudden, we have reached problems of pattern recognition. This is exactly why these kind of, say, tactical behaviors are more difficult than these purely reactive ones, because if it is just about observations of individual attributes and their values, whether it's low or high or whatever, that is something we can write down immediately. But if we have to incorporate temporal context and think about ways of how to deal with stuff that we may never have seen before, things get more complicated. Right? And because things are getting slightly more complicated, we'll have to spend slightly more times on these things, And in order for you not to lose track or to, well, you know, appreciate what we're going to do today, I'll first provide you with an outlook of things to come, so that you know what it is good for. That we are, no, it's not a question, I'm ahead of myself. What all of this is good for, that we are going to deal with today and next time. So here is an outlook. We will study in the next lectures to come the problem of modeling and recognizing. Right, if we have a model of something, we can verify whether that model is appropriate given a certain observation you're currently having. Modeling and recognizing temporal patterns. Temporal patterns. So what we're going to study works in general, does not only apply to observations of game entity attributes. Temporal sequences of attributes could also be applied to problems in the area, say, of speech recognition, where actually these kind of things play an important role. This is what we're going to study. And to prepare ourselves for that, we'll look into probability theory, and random variables. Random variables. We have to understand these concepts. And once we're sort of comfortable with that, we will look into something that is called graphical models. I'm not specifying that right now, but like once we reach that point, we'll study that in detail. And after that, we'll look into the notion of Markov chains. And once we're familiar with that, we can then finally study hidden Markov models. Hidden Markov models. See these in the H, M, we already saw. And when we are studying hidden Markov models, we're of course particularly interested in how to do inference with those. Inference, and I already said it, it's a pattern recognition technique, and you may remember or recall from our pattern recognition lecture that pattern recognition typically involves statistical training. So given lots of observations, hopefully labeled observations, we can train statistical models or implementations of world models that involve lots of parameters. We can use these labeled observations to infer suitable values for these parameters in order to train our models to what's really going on in the world. Once we have trained them, we can use them for inference. When we study this, we'll first look into the problem of inference, it's easier, and then we'll look into the problem of training hidden Markov models. So that is, of course, like should some of you ever enter the gaming industry, once we have studied that, you can actually tell them how to do tactical behavior. All right, so this is our menu for the next couple of lectures. Right? And we are doing this in order to understand this. And this we are doing because we are interested in the problem of modeling and recognizing tactical behaviors. The enemy is trying to conquer the base. How can we do that? And yeah, but in order to get here, we'll have to probably do this first. Okay, so that has been a long sermon. But now you know why I'm probably taking a huge step back at this point in time and address the area of probability theory. And I'm going to talk about this so that we are all on the same page. It is mandatory, actually. Once we're really looking into hidden Markov models, it really is helpful that we have reminded ourselves about these elementary ideas. Okay, of course, that may not be new to some of you, but we'll definitely touch on stuff you might not have seen before. Now, I already said it. In computer science, we have kind of these schools of thought. Funnily enough, I consider it to be ridiculous. And I said, you know, some people love fuzzy logic and reasoning and control and cast every problem they are dealing with in terms of the stuff we have studied last time. And other people detest that, and they rather prefer the use of probabilistic models in order to do reasoning under uncertainty. Now, the obvious question then is, what is probability, and like, you know, why would some people prefer that? Well, not really look into that, but the obvious question we will be looking into right now is, what is, say, a probability? And when we ask that question, this is another extremely funny thing, and this is actually why I brought up this sort of schools of thoughts regarding fuzzy logic or probability. Because I said, you know, we are not in the humanities, that is, to us, something either works or not, and so it's not, you know, I rather subscribe to this theory than to that one, because in the hard sciences we have in the end always mathematical proof. And in mathematics there are typically really no different schools of thought. Right? But why should there? Because you can prove everything or not. Either it's provable or not, and there's certainty in mathematics. But probability is something where mathematicians sort of diverge, where there are indeed two schools of thoughts or 2 points of view. 2 points of view. The first one is the, well, let's be careful, classical point of view, that is the so-called frequentist U. And under this, or from this point of view, a probability is the outcome or relative frequency. Probability is a frequency of a certain outcome in a long series of observations or trials. And the canonical example here is you are throwing a coin or rolling a dice or some gambling stuff like that. Say rolling a dice, there are of course 6 possible outcomes, numbers 1 through 6. And the question is how probable or how likely is it to observe the dice ending up with the number, say, 3 on top. Right? Of course, we know if the dice is fair, then die is fair, there should be 1 over 6, sort of 6 possible outcomes. If each of them is equally likely, we can immediately say, well, it should be 1 over 6. But if we, I don't know, do not make any assumptions as to the fairness of the die and we want to actually determine it from experiments, we could ask for the probability of it landing with 3 up. And so we would have to roll the dice, say 10 times, and count the number of times the 3 ended up on top. Right? And say that happened 2 times out of 10. So we would say the probability for observing a 3 is 1/5. Right? Well, now you would do it 100 times, and I don't know, it would come up 15 times out of 100, and you do it 1,000 times, or whatever. Like, you know, this is this ratio of how often you have done something, how often you have observed something, over how often you have actually done the experiment. That would be the probability for the particular outcome of that experiment. Right? Throwing a coin, how often does it appear coming out heads, how often does it come out tails. This is great, right? This is, so once again in the frequentist view, we have the long-term probability is sort of the long-term frequency of random events. How often, once again, do we observe a certain outcome if we carry out an experiment quite a number of times? In order to be really sure, we'd of course have to do it infinitely many times, which is rather impractical. But if something has been done, you know, thousands of times, that's probably actually a good idea as to how to define the probability of the outcome of an event. Because this immediately provides us with a way of measuring probabilities. Right? Now, last night, Costa Rica advanced to the quarterfinals in the World Cup. And we could ask for the probability of Costa Rica winning the World Cup. What would the frequentists say? Impossible. Has never happened before. There is no observation of Costa Rica ever winning the World Cup. So the probability, the long-term frequency in random events, like say every 4 years there is a World Cup, and I guess Costa Rica has appeared 4 times so far, and it's the 4th time, so the last 3 times they never won. So probability of Costa Rica winning is 0. Has never been observed before, cannot happen. That somehow violates our intuition, right? Why shouldn't they win? It might be very unlikely, granted, right? But is the probability 0? Who knows, right? And so therefore, there's actually a second view on probability, and this is the Bayesian view. Bayesian view. And seen from this perspective, a probability probability is a degree of belief in the truth of a proposition. Let me write that down. Is the degree of belief in the truth of a proposition. So the proposition could be Costa Rica will win the World Cup. We could say, well, that is totally unlikely. It won't happen. We can say that. Even though we have never observed them winning before, and so there is no way of sort of measuring this degree of belief. Well, if measurements would indicate this is unlikely, our degree of belief could also be this is unlikely, it will not happen. But this is, of course, more relaxed, right? Because we can assign probabilities, and we'll look into what that means, to things that have never been observed before. So you could immediately say, this is better. Why should we sort of enslave ourselves to this notion of probability that we have to measure ratios? Ratios of observations over number of trials. This is great. It gives us a way of measuring probability immediately. But it does not allow us to assign probabilities to things we have never observed before. So this seems to be better. Then why would mathematicians sort of either subscribe to this view or that view? Because here the obvious problem is like, okay, so what is the probability of Costa Rica winning the World Cup? And we still don't know. Right? So I can formulate a degree in belief, say 1/32, because originally there were 32 teams in the World Cup, and maybe it's equally likely that each of the teams will win. But in that case, even though we have never observed it before, probability of Costa Rica winning would be 1/32. Well, then you could argue, hey, wait a minute, it's so much more likely that Brazil will win, for whatever reasons, than Costa Rica. So, this 1/32 is probably optimistic, and you should sort of modify your your belief as to this proposition. So, what I want to say is that it's not immediately obvious how to, assign these probabilities, like how to measure these degrees of beliefs if we subscribe to this point of view. And this is the critique here. These guys say, well, you cannot talk about stuff you have never observed before. And they say, well, you can talk about these things, but it's not really principled how you do it. You have to somehow, rules of thumbs and assign degrees of belief to stuff and then take it from there. So this is indeed, and it's funny, an area of mathematics where there are 2 points of view. And the really funny thing is that they use the same methodology. Right? So it's like technically they are sort of indistinguishable, but this is rather philosophical. Now, in what follows, we will subscribe to the Bayesian view for 2 reasons. We will assume the Bayesian point of view for 2 reasons. First of all, everybody in machine learning does it, which is, of course, a very weak reason for doing it. The good thing about that is that if we assume the Bayesian point of view, it might be easier for you to read up on in the literature, right? Because typically in the area of machine learning and pattern recognition, people assign to the Bayesian point of view. But the more important reason is that it is indeed somehow simpler to talk about what is to come next if we think of probabilities as degrees of beliefs rather than of long-term frequencies. And you immediately see what I mean by that. So we can now sort of, in a very axiomatic way, approach the problem of trying to formulate an algebra of probabilities. So using very fancy terms here, algebra of probability. This is basically referring to the question how to compute with degrees of beliefs. And how to compute with probabilities, which, as I said, we understand as degrees of belief. So, and here sort of we diverge from what we did last time. Last time we talked about sort of this fuzzy, this way of introducing uncertainty into reasoning. And of course, like from the terminology we have been using so far, it appears this is, degrees of beliefs is also something rather fuzzy, something, I don't know. I mean, I believe that Costa Rica will win the World Cup 0.278. This is my degree of belief. I don't do that. I say something like I'm fairly certain that they win, or fairly certain that they will not, or I'm really undecided. Again, when we talk about things like that, we do so in a rather fuzzy way. But the concepts we are going to look into right now are different from the ones we studied last time. Now, the first thing we have to decide when we want to compute with probabilities is, again, we have to, come up with numbers. Right? If we want to compute with something, it's good to have numbers or something we can manipulate mathematically. So we have to think about the following aspect. Transitivity. Say there are three propositions, A, B, and C. And I would say that I believe B more than A and C more than B. All right, so we have I don't write down. Three propositions, A, B, and C. And I believe B more than A and C more than B. Well, then it makes sense to say that I believe C more than A. Right? That there should be this property of transitivity. And that, in other words, is to say that degrees of beliefs can be ordered. There is an ordering relation. Right? And then the question is, okay, so then we can think about degrees of beliefs in terms of real numbers, right? Because there we have this ordering relation, less or equal than. But should we say that if we do not at all believe something, the degree of belief is minus infinity? Or is it minus 20? Or is it 0? And if we believe something for sure, is our degree of belief 1 or 15.8 or infinity? So we have to fix the interval for the degrees of belief. And we fix it to the interval between 0 and 1. So the probability of false is 0, and the probability of true is 1. And I probably should write it in a different manner. You can squeeze it like in your notes here. Just squeeze this in here. Probability of true is 1. So we have this ordering relation for the degrees of beliefs, and now we have fixed the smallest degree of belief we can ever have to 0, and the highest degree of belief we can ever have, we have fixed that to 1. That looks arbitrary. It is not. There are really deep philosophical and mathematical considerations attached to that. Indeed, like a guy called Cox, I don't know when that was, in the 1940s also, proved mathematically that that is a good thing to do. That is a good thing to do. So if we totally do not believe something, this is disbelief, it will not happen, or it is just not possible, then we assign a probability of 0 to that. And if we, like, on the other hand, totally believe something, we are certain that this is so, then we say the probability is certainty is 1. Okay, so we have fixed the interval about which we are talking when we are talking about values of probabilities. Now, the next thing to think about is how to manipulate probabilities, how to compute with them, right? And think of it like this. So we'll have this property of closure. We already looked into transitivity. Now we look into a property called closure. If I say Costa Rica will win the World Cup, the probability of Costa Rica will win the World Cup is 0.2. We now know this probably has to be something, or should be something between 0 and 1. And I say my belief in the truth of the proposition that Costa Rica will win the World Cup is 0.2. Then, without having said it, I implicitly specified my disbelief, right? Because that can be like the belief is something between 0 and 1. And if I believe in them winning the World Cup with a probability of 0.2, then I believe that they will not win the World Cup with a probability of 0.8. Right? So implicitly, if we state our belief in the truth of a certain proposition, we implicitly state our disbelief as well. Right? And that is to say that the probability of a certain proposition x, and x now refers to, say, Costa Rica will win the World Cup, plus the probability of not x should sum to 1. If we agree that something happens or does not happen, and if we assign a number to either of these two things, then we implicitly assign a number to the other. Right, this is the probability property of closure, and that also goes by the name of the sum rule of probability theory. Okay, we have now elaborated on two aspects of computing with probability, and here is another one. We have to think about the concept of conditional probability. Conditional probability. And that is to say, I'm just, sketching it. If we first state our belief in the truth of a certain proposition, and then, once we have stated that probability, state our degree of belief in another proposition, given that the first one has happened, or is true, we implicitly state our belief of both of them being true at the same time. And this is indeed probably easier written down mathematically than paraphrased. So we say that the probability of x and y, note that this comma here has to be read as and. Right, we have two propositions. Costa Rica will win the World Cup. Weather in Brazil is hot. And now we ask for the probability that Costa Rica will win the World Cup and the weather in Brazil is hot. This is a stupid example, as we'll see in a second. But this is how we have to read this. Right? There are two propositions, and this comma means and. So this probability can be expressed as the probability of y and then the probability of x given y, so times p of y. And this is what I paraphrased. We first state our degree of belief in the truth of a certain proposition y, and then state our belief in another proposition given that y is true. And when we look at a product like this, then we basically talk about our degree of belief in both propositions being true at the same time. This is called the product rule here. It's like called the product rule of probability. Product rule. And in a sense, all of these things we have looked in so far can be thought of as axioms. Right? So they do indeed make sense, but we can take them as given. We probably should, because otherwise it really gets philosophical, and if you read these texts by Cox on the philosophical underpinnings and logical underpinnings of all, that all makes sense, but let's not look under that rock. Let us accept that a probability is a number between 0 and 1, inclusive, so could be 0, could be 1. That we have this sum rule, and that we have this concept of conditional probability, and that this sort of leads to this product rule. These things, let us accept them as axioms. Once we have those, we can derive many other ideas from those three things. And an extremely important one is Bayes' theorem. The guy called Bayes' theorem. This is the Bayes in the Bayesian view of probability. He sort of, I don't know, was the first, but one of the pioneers of thinking about conditional probabilities. So we just said that the probability of x and y, two propositions, can be factored as the probability of x given y times the probability of y. This is sort of axiomatic, say, but if we write it down like this, we sort of have a preferential treatment of x, right? X here is conditioned on y. Why should that be? There is no reason for that. Right? This, like, you know, if we have probability of x and y, can factor it like this, but if there is no reason for us to think otherwise, this should be the same as the probability of y given x times the probability of x. Right? Otherwise, we would treat one of the two propositions differently than the other. That can happen. I'm not saying that there are situations where it shouldn't be the case, but typically we should think that this is the same. Now, if this is the same, then we have the following theorem, and this is immediate, and this is Bayes' theorem, that the probability of x given y can be written as the probability of y given x times the probability of x over the probability of y. And of course we can rearrange these things, but this is Bayes' theorem. This, in the pattern recognition lecture, we talked about the fundamental importance of this, because and how that would allow for inference processes. And we can think of it like that. Say that y would be a sequence, an observation we make in the real world, some data, right? And we would think that whatever we measure has had a cause, so something caused it, and we would have models for different things to happen. I don't know, say a model for enemy is approaching or is trying to conquer the base, and enemy is fleeing. So there's two models of what can go on. Say in the easiest case, just two different things. And now there are observations, and we want to sort of infer, given these observations, what is going on. Now, we could ask, say, y would be the data, and x would be the, I don't know, say hypothesis or model. Make it hypothesis. So we want to know, we have two possibilities here. We observe something. We want to know which of the two possibilities is more likely, which has the higher probability. Possibly difficult to say, but we can turn it around. We can say, so if, say, the enemy is fleeing, then this leads to the following data. This is something we could probably simulate. We could simulate as a game AI entity. We could simulate how does it have to look like if the enemy is fleeing. That would generate some data. So we would have the data given that the enemy is fleeing, then times how likely it is that the enemy is fleeing over how likely it is to observe the data. But we can turn around, using Bayes' theorem, turn around the question of what is going on given some data. We can express that as if something was going on, then how would the data look like? So we can use this for inference, right? So again, in this example, we would simulate how does it look like if the enemy is fleeing, how does it look like if the enemy is trying to conquer the base. That would allow us to attach a value to the right-hand side of this equation, and that immediately allows us to deduce values for the left-hand side, and then we have one value for enemy is fleeing given the data, and one value for enemy is trying to conquer the base given the data. And whatever has the higher probabilities, probably that's what's really going on. So this is useful for inference. Okay. Now, in all we have seen so far, it was with respect to two propositions x and y, or x and not x, whatever. Let's ever so briefly generalize this. Generally, so we could think of, I don't know, the probability of x and y and z. This is not really general, it's just one more. But it's just to show you how that would work. Now, this is the joint probability for all these three propositions. How could we factor that in terms of conditional probabilities? Okay, we could say this is the same as the probability of x given y and z times the probability of y and z. It's just one application of the product rule, and I put a for instance here. Now if we have that, then here is another joint probability. Maybe we can factor that further. So we would have the probability of x conditioned on y and z, say times the probability of y conditioned on z times the probability of z. So this is just applying this product rule a couple of times. In this case 2 times. We had 3 propositions. Like if we had more here, I could do that with many lines of writing it down. You see. And I said, for instance, because now it would appear again that I have treated x in a preferential manner. It always depends on what we are really going to do with expressions like that. This is, of course, not the only way how we could factor this joint probability. I could just as well do it like p of, say, y given x and z, and then times p of x. Now make it actually the other way around. Z given x times p of x. Right? This is. I'm making this point because and we'll see expansions like that, quite a lot in the next couple of lectures. And when you see that, and I will do this like hundreds of times from now on. That does not mean that this is the only way. Like we have this joint probability, and let's factor it like blah blah blah. It's not the only way. We can also factor it like this, and if I use a certain factorization, then that typically is because here this is just general letters x, y, and z, and there's not really something attached to it. But of course, when we use these things in practice, then there are real propositions or events referred to by these let's call them variables, and then of course we might know that certain things are indeed conditioned on other things and not vice versa. Right? But like in its very generality, we can do any sort of possible permutation here. So don't be alarmed that I will always write this down basically in a sequence from left to right. Later on, I will order like the random variables we are talking about, always like in that sort of sequence in which they are conditioned on one another. Okay, I'll erase all of this and keep that for instance over there, because now you might be tempted to think that when we sort of apply the product rule to joint probability like that, that is always a single variable that is conditioned on a tuple of variables, but that of course does not have to be the case. I could just as well factor this as p of, how do I have it here, x and y given z times p of z. And this is for instance because just as well we could probably also factor that as p of y and z given x times p of x and so on and so forth. So there's like several points of how to do that. Now, and because this really like this will keep us busy for days to come from now, here's a little trick. Like why would I write this down? Like, and how could you map these things to the product rule, or how could you immediately, I don't know, write down some Bayesian rearrangement of terms? Here's a trick. trick. So let's say we're given a joint probability of 3 propositions, events, whatever, x, y, and z. We can always think of, I don't know, 2 of them being aggregated into another proposition. So just think of, I don't know, W is x and z. I have introduced a new proposition, and then you know this joint probability of x and y and z can now be written as the probability of x and w, and this has only 2 propositions, and in every of the axioms we wrote down we had only 2 of them, right? And now you have artificially reduced this situation to that situation, and once you are here you can apply all the rules we discussed so far. Of course, which of the things you aggregate into a new one is to your liking, but you can always do that. Right? So if these are 3 propositions, lecture starts at 9, it is a sunny day, Costa Rica will win the World Cup. You can combine it's a sunny day and Costa Rica will win the World Cup into it's a sunny day and Costa Rica will win the World Cup. Let's call that W from now on, right? And then you have mapped this to this case, and for this case you know the algebraic rules. So don't worry, when we have lots of propositions and I'll do lots of expansions, then you can, if need be, always sort of reduce it to this and take it from there, okay? All right. Okay. 2 more things, and I guess then we are done for today. Let's think about the concept of marginalization. And basically consider this. So let's look at the conditional probability of y given x and plus the conditional probability of not y given x. What should I write on the right hand side of this equal sign? No. Can we infer something about x from this? To make it short, no, we can't.
Oh, it's 1 then.
It's 1, exactly. It's 1, right? Because what this says is, this is our degree of belief in the truth that x is y is true given x, plus sort of 1 minus that, right? Because this y is not true given x. Well, one of these 2 things has to be given. So if we leave that with 0.2 and this with 0.8, well then, I mean, together these 2 things have to be 1, right? Has to be, because it does not really matter whatever x is. One of these 2 things sort of should happen. Either it is true or it is not true. And if we add our degrees of beliefs in the truth of something, regardless whatever we assume, if we add these 2 things, should be 1. And this is sort of like really independent. This expression is independent of what we condition upon. Now, but if we have this, we can think of the following. We can ask the question like, okay, so then let's say the joint probability of x and y plus the joint probability of x and not y. What is that? we are interested in the right-hand side of this equation. But before we write it down, let's apply the product rule. So this is the same as, just to see how these things come about, this is the same as P of y given x times P of x plus probability of not y given x times probability of x. Now we factor out this P of x, so we have P of y given x plus P of not y given x times P of x. Now what is on the right hand side of this equation? Well, so basically we are interested in the sum of these two joint probabilities. What do I have to write here now?
P.
Exactly. Right? Because we have just seen that this indeed will evaluate to 1. So whatever's in the square brackets here is 1. And 1 times P of x is P of x. And that is to say that if we have a joint probability x and y, and let us assume that this y can assume different values, so like either it rains today is true or it is false, but can also be, let's come up with some more involved propositions. The outcome of rolling a dice is 4. We know that there are 6 outcomes, so let us assume we have, I don't know, some proposition x and some proposition y, which refers to the outcome of rolling a dice. And we are looking at the joint probability of that. And now this y can actually assume different values. I will refer to that as yi. And we sum over all possible i's. Then this is independent of y. And this is called marginalization. Right? So we have a joint probability, and for one of the variables or propositions we are interested in, we sum over all possible outcomes of that variable or that proposition. And then the joint probability, if we do this summation, does indeed not depend on, in this case, y anymore. And now we talk about independence. Independence. We basically say if x and y are independent, then the joint probability, our degree of belief in them both being true at the same time, can be written using the product rule as, say, P of x given y times P of y. But we said they are independent, and that is to say the degree of belief in the truth of x should be independent of whatever y is. Right? And if they are independent, then this conditional probability can be written as P of x, because probability of x given that y, if they're independent, probability of x given should be probability of x. X is not conditioned on y whatsoever. So for instance, x is, the lecture starts, x is, it's a sunny day, and y is, the lecture starts at 9 o'clock. At very first sight, those two things have nothing to do, they are independent. Right? So whether or not it's a sunny day is totally independent of when the lecture starts. Just like that. So this would be P of x times P of y. This is what defines independence. I have weather is bad because weather might actually influence whether the lecture arrives on time or not. What about the lecture starts at 9 o'clock and the lecture is interesting? It's probably like now really independent. Whether like when it starts is independent from whether or not it's interesting. Maybe. But weather might actually influence the start time. We also write x independent of y. This is this is another way. So instead of writing down x and y are independent, you might find that. Okay. Now, great. Conjoint probabilities, we now know, at least have seen the concept of independence. What about conditional probabilities? Could we think of something called conditional independence? And if I am asking in such a suggestive manner, then of course the answer is yes. So now we look into conditional independence. And we do it like this. We consider x, y, and z. If the conditional probability, let's say, of x given y and z, if this probability does not depend on y, then, this is to say, this is basically sort of the same notational trick we just saw with joint probabilities. Then this conditional probability P of x given y and z is just the probability of x given z. It's just what we saw previously, this time with conditional probabilities. And we say that and x is conditionally independent of y given z. So this is again such a very long sentence, and since we do not want to write down this sentence all the time, we write x is conditionally independent of y given z. Okay. Now, the question at this point in time is, why should we study conditional independence? Because now we have reached sort of the final point I wanted to make today. This was all just a very quick and brief refresher of elementary concepts of probability theory. Now we are all on the same page. Now we can dive into the study of conditional independence. This is something might be less well known than the things we have done today, but at least we are now prepared to study that. Right? And we will. This is what we are going to study next time, the idea of conditional independence. Well, you might be asking why. the easiest answer to that is hidden Markov models are all about conditional independence, right? And then you could say, oh, why? I mean, okay, now I have answered why we should study conditional independence, because we want to study hidden Markov models, because we want to infer activities within a game world from series of observations, and I said we use hidden Markov models for that. And now we know why we should study conditional independence, but you should ask, well, then why are hidden Markov models all about conditional independence? That is a much more valid question, and well, there the answer is basically ease of implementation, ease of modeling, ease of reasoning. I know that with some of you I have already discussed issues related to conditional independence. And the question really is like, why would we model things, and we'll see how that goes, using conditional independence assumptions? And really the answer is, it becomes doable. It becomes feasible. We can, when we want to model behavior using probabilistic approaches, we can think about tremendously complex models, right? And sometimes those have their merits, but the more complex our concept about something is, the more difficult it will be to implement that concept on a machine and to actually compute with its ingredients. And indeed, it might take quite a long time to, process that model and come up with the answer, oh yeah, the enemy is approaching the base. So we for practical reasons, we might want to prefer simple models over more involved ones. And we will see that for this reasoning about temporal observations, simple models, in the sense of that they heavily rely on the idea of conditional independence, are indeed good enough to allow us to cope with the problem of inference or about temporal patterns, and therefore modeling and recognizing enemy activities. So that is why we study conditional independence, and just from looking at these crazy expressions here, that is not really apparent, and it's not really at all clear what that really means, in particular what this means. So next time we will look into that a bit more closely. Once we are done with that, we can study Markov chains and hidden Markov models. That is all for today. Are there any questions? If not, then see you on Thursday.